we need to solve one-dimensional problems involving the relativistic addition of velocities. First, we'll look at the Galilean transformations. So let's do this using the relativistic equations. Now, the IB like to do it this way. They like to take the other frame of reference and do all the measurements, do all the calculations, do the calculations from the second frame of reference. So we have our frame of reference is here with our car moving at the speed of u in this frame of reference. Then this car is static in this frame of reference, which is moving to the right of a speed of v. Of course, it's going to be negative v. So the Galilean transformation is going to be u prime is equal to u minus v. So, in other words, this car's measurement of our car is going to be u prime is equal to the speed of u, which is our speed of u, measurement of u, which is our measurement of the speed of the car in our frame of reference, minus the speed of the second frame of reference. So it's going to be 0.7 to the right, negative 0.7 because the frame of reference is actually going to the left here, and it gives you a value of 1.47c. Okay, so there is agreement there, but 1.4c is not possible. So u is the measurement as u is the velocity as measured in the first frame of reference. U prime is the velocity of our car as measured in the second frame of reference. V is the velocity of the second frame of reference as measured from the first frame of reference. And this is the equation that we need to use. So we do u minus v, which we've already calculated to be 1.4c, divided by 1 minus u times v. Remember, u is plus 0.7, v is negative 0.7c, divided by c squared, and we end up with a value of 1.4c divided by 1.49. So it ends up being almost the speed of light, but not greater than. Okay, one easy way of looking at this is that if the objects are moved in opposite directions, in other words, towards each other or both away from each other, then the relative velocity is greater than their individual velocities, but it will be less than c. If the objects move in the same direction, the relative velocities will be smaller because one will be subtracted in some way from the other. And this is the equation we should use. And this is as it stands in the data booklet. U prime is the speed of our car as measured from the other frame of reference. Ux is our measurement of our car from our frame of reference. V is the speed of the other frame of reference relative to us. An example, two approaching electrons, each travelling at 0.9 c. So we would use, which one do we use? We would use the second one here. So we have this frame of reference. The first electron is travelling at 0.9 c to the right. The frame of reference of the static electron in the second frame of reference is moving to the left of 0.9 c. So we have to take the view of our frame of our speed of our electron from the other frame of reference. So we take this equation, u prime, which is their measurement of our electron, is 0.9 c because that's our measurement of our electron relative to our frame of reference, minus negative 0.7 c, not 0.9 c, which is the measurement of their frame of reference relative to us, and then we subtract their divided by 1 minus 0.9 c times by negative 0.9 c, because remember the v is going backwards, divided by c squared, and we will end up with an answer of 0.947 c. So you should try that out and see if you end up with the same value. Here is another question. You have a space rocket is moving to the left at 0.8 c, and another one is moving to the right at 0.8 c as well. an observer on the ground measures the separation as being 1.60 C. That's fine, as long as any particular person doesn't measure something else that's going away from it at greater than C. So you calculate the speed of one spacecraft relative to an observer in the other. So we use this equation. U is going to be our measurement of this this spacecraft, which is going to be negative 0.8. V is the speed of their frame of reference, which is going to be plus 0.8. So it's going to be negative 0.8 minus plus 0.8, so it's going to give a value of 1.6 C. And then we do the same calculation there, and you should end up with a value which is going to be greater than 0.8 C, but it's going to be less than 1 C.